This is a related continuation of the previous two videos I had uploaded on ordered hashing 8 and another one on information coding for error detection and correction. In this video, for the second hash function, which is of the form r power s minus v plus 1 into m less than equal to k, we can calculate r either as r equal to 1 by m, that is equal, which will be not necessary. We can take it as 1 by square root of m or cube root of something like that. That is sufficient. What you can do is you can also use hashing by parts. You can divide m into p parts of the form m is equal to mp minus 1 whole power p minus 1 plus mp minus 2 whole power p minus 2 and so on up to m naught, and s also similarly as sp minus 1 whole power p minus 1 plus sp minus 2 whole power p minus 2 plus and so on plus s naught. The only thing you have to remember is if you have got a value vi of the form r power si minus vi plus 1 times mi less than equal to ki is also divided into p parts, then if you increase the value of vi plus 1 to vi plus 1 plus 1 more, the difference between those two must be composed with this value of m that you get to get a new value of 1. This should be m dash. mp minus 1 will be that difference for the new value. So that doesn't, that may not be much. So you can combine it by parts this way. The other thing with the problem with the other technique I suggested was finding the sum for, well, just taking the summing of the indexes in order to find the sum, and while maintaining the one count. Their collisions can easily occur there because, again, due to the law of commutativity, that is a plus b equal to a plus c plus b minus c. So if you add 1 plus 4, it is the same as 2 plus 5 or something like that. Keep the one counts, then the probability will reduce. Another possibility which doesn't help is trying to minimally increase the weights you assign to this, so that for for a given any particular R combination, the sum never is the same. The sum can be the same for different R combinations. So for different values of R, you try to do that. So you can try to approach that combinatorially as well, but that may not help as much. Another simple idea which can be used to overcome this problem is if you just sum up the values 1, 2 and so on up to L dash minus 1 as the weights you use to sum up, rather than 2 power 0, 2 power 1 and up to 2 power L dash minus 1, chances of collision will increase. You can decrease it by what you can do is mapping these values to some permutation of this. If there are L dash, means there are factorial L dash permutations will be very, very large. But you are only interested in some permutation, the one that and then sum up as well, maintain that sum as well throughout the tree. So for this sum again, so only up to a certain very small depth such as 8 or 12 or 16, something like that, for a very slight. If the permutation, a simple permutation is, since we are always dividing by halves, we could take up something like 1 then say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So now the you, in addition to maintaining the former sum which is like that, you also maintain this sum. Now if the shift occurs there, because the displacement there is not plus or minus 1 but different one for different this thing. So if two bits shift equally, but if they shift unequally, the probability of the sum adding up will be still be there, but nevertheless this will reduce the probability of, since the average distance between any of two of these will be slightly large. So any 2 or 3 bits, the sums adding up will be very small. So this way you can try to make improvements to the design. In general, if you want to check for possibility of error without correcting it, these kinds of methods can be used.